In this video, we're going to give a proper definition to the idea of an interpretation of a first-order formula. But before I do that, I'm going to introduce certain collections of numbers whose notation I've written on this slide, because we'll use those collections of numbers very often in our work on first-order logic. So I'll begin with this funny bold N symbol right here, which represents the natural numbers. So natural numbers are numbers like 0, 1, 2, and so on. Now, some people don't include 0 in the natural numbers. It really doesn't make any difference to the truth or falsity of anything we're going to do. So for me, 0 is a natural number, but it doesn't really matter whether it is or not. The next set of numbers we're going to talk about is the integers, written with this bold Z symbol here. So the integers means all positive or negative whole numbers. So things like -3, that's an integer. 3, that's an integer. 0 is an integer. 50,000 is an integer, and so on. So any positive or negative whole number, that's what the integers means. Next we have the rational numbers, which we write with this symbol Q. And rational numbers just means all the fractions where the numerator and the denominator is a integer. So all things like 2 divided by 5, and 6 divided by 7, and -6 divided by 2, and -6 divided by 5, things like this. So any fraction where the things in the fraction are whole numbers. And of course, you're not allowed to have 0 as the denominator. Finally, the last set of numbers we need is the real numbers. The real numbers are just every number with a decimal expansion. So it includes all the fractions, things like 2 over 5 and 6 over 7 and so on, and all the negative fractions as well. And it also includes things which are not fractions but which do have a decimal expansion, like pi and like e and like the square root of 2 and like 1 plus the square root of 5 over pi, everything like this. So absolutely every number with a decimal expansion. Okay, having done those definitions of certain sets of numbers, let's move on to the definition of an interpretation. So here it is. An interpretation of a first-order formula consists of two things. So first of all, a set which the variables of the formula will belong to. And that set has a special name, the domain of the interpretation. And secondly, for each relation symbol in the formula, you have to give a relation on the domain of the interpretation. Let's see a couple of examples of that. So we'll begin with the first order formula here that says for all x, p of x. So here we have a variable symbol x, we have a relation symbol p, we have the quantifier for all. So there are lots of different interpretations of this formula. Let's give a couple of them. So the first interpretation might be we take the domain to be the set of rational numbers, so the set of all integer fractions, and then the relation p of x, that has to be a true or false statement about one rational number x, so we might make that x squared is equal to 2. Then the way we write the interpreted formula is like this. We write the interpreted formula as for all x, and then this symbol q, and that means for all rational numbers x, x squared is equal to 2. Okay, this is definitely a false statement. Certainly not true that every rational number has a square equal to 2. Okay, let's move on and look at another more complicated first order formula. So this one here, for all m, there exists n such that p of mn. So this time we have two quantifiers. We have the universal quantifier, the upside down a. We have the existential quantifier, the there exists quantifier, which is the backwards e. And we have two variable symbols, m and n, and we have a relation p, which is a relation between two things, so a true or false statement about two things. So a possible interpretation for this would be we take the domain to be n, the set of natural numbers, so 0, 1, 2, 3, 4, and so on, and then we make the relation P of mn be, let's say, n is greater than m. Then the interpretation we write like this. So for all m in n, that means for all natural numbers m, exists n in n. That means there exists a natural number n such that n is greater than m. Okay, so you might like to think about whether this formula is true or false in this particular interpretation. We'll come back to this later and I'll tell you what the answer is, but it's a good thing to think about to test your intuition of the meaning for these quantifiers and for these quantified statements. So we've now looked at how to interpret a formula, and the point of interpreting formulas is that a first order formula is not true or false on its own, but once you give an interpretation of that formula, you can decide whether or not the first order formula is true or false in that interpretation. And of course, in general, in some interpretations the formula will be true, in some the formula will be false. So let's look at how we do this. So there are some rules for when a formula that begins with a quantifier is true or false in a particular interpretation. So here is the rule for the for all quantifier. If you have a formula which begins with a for all quantifier, and you have an interpretation where the domain is a set A, then the interpreted formula, which would look like for all x in A, something, so phi just represents the rest of that formula, that interpreted formula is true if and only if, for every element of the set A, when you substitute A into phi in place of x, you get a true statement. So let's, before we read the second part of the definition, let's just look at what this, what's going on there. So for example, you might say, we might have a statement like, for all x in Q, x squared is equal to 2. That's an interpreted first order formula. We wrote, this is the same one we looked at on the previous slide. And this is not true, because it's not true that for every rational number Q, every rational number, let's say a squared is equal to 2. Right? It's definitely not true. I mean, there's not even any rational number that makes that true. So this is false. Let's look now at the next bullet point, which is about when an interpreted formula that begins with the there exists quantifier is true. So an interpreted formula where the domain is a set A that looks like this, and here again phi just means whatever the rest of the formula was, that thing is true in an interpretation if there exists an element in A such that when you substitute A into phi in place of x, you get a true statement. So for example, let's look at something like, let's say we had an interpretation which looked like there exists x in R such that x squared is equal to 2. Now, is there an element A in R that's such that when you substitute A in place of x, you get a true statement in this part here, so the remains of the formula? And the answer, of course, is yes, right? This definitely is true, because there is a number, a real number, that makes x squared equal to 2 true, right? The square root of 2 is a real number. So this thing is true because you can find a real number, namely root 2, whose square is equal to 2. So where these rules get more complicated is what happens when I have a statement with more than one quantifier in it. So you've seen an example of this. We had an example first order formula which was for all m exists n such that p of m n. And then in order to determine the truth of a formula like this in an interpretation, we then have to use both of those rules. So first the for all rule and then the exists rule. So we'll do some examples of exactly how you can determine truth or falsity of complicated formulas with more than one quantifier when we have an interpretation for that formula. So let's look at some example interpretations. So we have here the formula, which I've called f, and what f is doing, f is the first order formula for all m exists n p of mn. So let's look at some interpretations of that formula. We're going to look at two different interpretations of the same formula. So in our first interpretation, what we'll do is we'll take the domain to be the natural numbers n. So that means in our interpretation, the variables m and n can be natural numbers, and we will take the relation p of m n to be the greater than relation. So this is m is greater than n. When we do this, the interpreted statement becomes, so the interpreted formula, well, we write the interpreted formula as for all natural numbers m, there exists a natural number n such that m is greater than n. Okay, so we now can decide whether this is true or false. And to decide whether this is true or false, we can use the rules for determining the truth or falsity of interpreted statements that begin with the for all quantifier. So what we're asking here is this true? Well, we need to check, is it true? So is each one of the statements exists n in n such that m is greater than n true. So for every m in n. And of course, the answer to this, well, pause the video and think about it for a moment. The answer to this is no, right? This is not true. So the reason it's not true is because if you take m to be 0, for example, there is no natural number which is less than 0. Okay, so this formula was false in this interpretation because the statement that there exists a natural number which is less than 0 is false. Let's look at a second interpretation. So we'll again keep the domain to be the natural numbers, and we'll just flip the sign of the inequality. So the relation, the way we interpret the relation symbol p, will be m is less than n. So the interpreted formula becomes for all natural numbers m, there exists a natural number n such that m is less than n. So again, we want to decide whether or not this is true. So, because this is an interpreted statement that begins for a for all statement, with the for all statement, what we're trying to figure out is it the case that, let's put it this way, are all of the statements there exists n in n such that m is less than n, so n is bigger than m. So when I say all of the statements, I mean for all possible natural numbers m. And the answer is, of course, yes, these are all true. So yes. Because if m was 0, then you could take n to be 1. If m was 1, then you could take n to be 2. If m was 2, then you could take n to be 3, or 5, or 1,000,000. And whatever m was, you can always find a larger natural number. For example, you could take n to be m plus 1, and that is bigger than m. So there's an interesting thing about these quantifiers, which you might have picked up on as we've been thinking about the meaning of for all and there exists. Let me make a little box at the top here where we can talk about it. So we've been talking, we had some simple examples where we looked at things like exists x, p of x. And if you think about the rule for interpreting, for determining the truth in an interpretation of a formula that begins with there exists, then the interpretation would be something like there exists x in whatever the domain is, such that p of x is true. So this is a bit like saying that p of a1 or p of a2 or p of a3 and so on is true, where a1 and a2 and a3 are the elements of a. So you might think, well, can I just do this? Can I get rid of all these horrible quantifiers and just think about or statements instead? Well, the answer is no, you can't do this, and it doesn't work. So what we're talking about here does not really work. In fact, it doesn't work. And the reason is, well, there are two reasons. The first is that, for all you know, maybe the set in the interpretation is actually infinite. So this so-called formula would have infinite length. You're not allowed to have formulas of infinite length. So this or statement that I wrote down just wouldn't work. And in fact, almost always in first-order logic, not always, but almost always, we're interested in interpretations with an infinite domain. And in fact, it's even worse than this, because if your domain was something like the real numbers, it's not even possible to list all the real numbers as a1 and a2 and a3 and a4, because the real numbers are uncountable. So you can't do this. It's kind of an intuition which you could use. So it's saying that there exists x in A such that p of x is saying that one of the statements, p of A, is true, but you can't really form this potentially infinitely long formula. And similarly, sometimes people think, well, isn't this really just the same as saying p of A1 and p of A2 and so on, where the A1, A2 and so on are the elements of the domain A. But for exactly the same two reasons, you can't really do this. So it's a kind of guide as to what those quantified statements mean, but it's not literally true, and that's the reason why we have to have these rules for interpreting truth in an interpretation. Let's look at another example interpretation, and this one is actually very similar to the previous one, except that I've swapped the quantifiers over. So before we had for all m exists n, and now we have exists m for all n, p of mn. And we're going to look at a couple of interpretations for this formula and determine the truth or falsity of the interpreted formula. So let's begin with, again, let's take our interpretation's domain to be the natural numbers, so all of the non-negative whole numbers. And this time we're going to take the relation p to be that p of mn is m being greater than or equal to n. Again, this is a legitimate relation on the set of natural numbers, because for any two natural numbers m and n, either m is greater than or equal to n or it's not. So it's a true or false statement about a pair of natural numbers. And we want to decide the truth or falsity of the formula in this interpretation. So let's write down the interpreted formula. So the interpreted formula says that there exists a natural number m such that for all natural numbers n, we have m being greater than or equal to n. So that's the interpretation of this formula, and the question is this a true statement or not? You might want to pause the video and think about it. So, is it true or not? Well, the answer is no. It's false. So the reason that it's false is because for this to be true, remember this is a statement that begins with an exist quantifier. So if it were true, one of the statements for all n in n, m or n is less than or equal to m would have to be true. So when I say one of the statements, I mean for all possible values of m. So one of the statements where m is some actual natural number would have to be true. But none of those statements are true, because the statement says that m is greater than or equal to every natural number, but there's no natural number which is greater than or equal to every other natural number. So the formula is false in this interpretation. So again, for our second interpretation, let's stick with the domain being the natural numbers. And we will make the relation be, again, the same thing, only with the inequality swapped over. So the domain is the natural numbers, and the relation, the interpretation of the relation symbol p, is that p of mn is going to be interpreted as saying that m is less than or equal to n. So the interpreted statement is that there exists a natural number m such that for all natural numbers n, we have m is less than or equal to n. So is it true? So what we're asking then is one of, or at least one of, the statements for all n in n, m less than or equal to n, true. So you get one such statement for each natural number m, and all we're asking is one of those statements true? Is there a natural number m that makes that true? So that's what we're asking. What's the answer? Well, again, pause the video and think about it. Of course, the answer is yes. One of those statements is true. Specifically, when m equals 0, this is true. Because every natural number is greater than or equal to 0.